All right, so last time we were talking about crystal field theory, and remember, in crystal field theory, we were just kind of having a generic metal, right? And then we brought some ligands in, and that caused repulsion of some, right? The yellow went up, and then the other ones went down, and so it's a good way of explaining, right? It's a good way of explaining just the basics, but what we need to get into is what's known as ligand field theory. Now, ligand field theory is basically crystal field theory. So we take crystal field theory and we add molecular orbital theory into it. Okay. Now, I was doing this a little bit last time already, right? I was doing this a little bit last time already when I was drawing you guys the pictures of things here, okay? And really in crystal field theory, we just assume a uniform field around the metal and then bring it in on the axis and all this kind of stuff. So crystal field theory, ligand field theory, pretty related, okay? But here's what we want to do, right? So let's say that we have a generic metal, right? We'll come back to one, right? A generic metal, and we have a set of ligands in an octahedral set around the metal, okay? So, just draw this out real quick, right? Let's say we have our friend metal right there. And we've got our ligands that are going to be coming in an octahedral set, okay? So we got... Now, we're going to make a couple of assumptions. First assumption we're going to make, we're going to start with doing a sigma-only ligand set, okay? We're going to do a sigma-only ligand set. Now, the reason why is because this will be kind of, let's say, the simplest of examples, and then we'll come back and we'll make it a little bit more complex as we go through, okay? That means a couple things here, right? So when we're doing a sigma-only ligand set, essentially what we do is we assume, right? So we assume a certain set of orbitals on the ligands, all right? Now, here's where I'm skipping a couple months of work also, right? So, we've got a couple different sets of orbitals on the ligand. So, for instance, let's say that, this is just a chlorine atom, okay? Or I should say a chloride. That means on this chloride, we have S and we have P orbitals. Technically, we have D orbitals too, but let's ignore those for now. What we would do if we're doing this completely, we would take our S and our P orbitals and we would take them all into what's known as a symmetry adapted linear combination, right? So what that means, and let me see if I can summarize a very complex idea here in 60 seconds. We would take a look at how our orbitals arrange themselves in three-dimensional space and assign a symmetry operation to that. For instance, right? If we had only, right, if we looked at only the s orbitals for all the chlorines, okay? So imagine that I'm drawing only the s orbitals here for my chlorines, okay? This is how they would look. All 6 of the chlorines have s orbitals. They would interact with the s orbital on the metal, right? And those have a certain symmetry with them. In fact, right, we would say they have an A1G symmetry. Okay, where the A means something, the 1 means something, and the G means something, right? I talked a little bit about that in the last time, okay? And if we went through and we looked at all the different combinations of the orbitals, and we did we looked at character tables and all this other kind of stuff, we would come up and figure out that we have an A1G set, we have an EG set, and we have a T1U set. Okay? Now let me pause here for just a second. What in the world does all this mean? Well, I have one A1G orbital that comes from, I'm only talking about my ligands, okay? I have one A1G orbital. Remember, the E in EG means we have a doubly degenerate. Say, okay. So we have two orbitals that are Eg, and we have a T1U, which means we have three. Okay? Who cares? What does this all mean? Right? Well, here's what's going to happen, right? So there are my sets of ligands that I kind of hand-waved out of nowhere, right? And don't worry, I'll give you guys a representation of these in just a little bit, okay? So just hang on to your thoughts for just a minute, okay? So there are the orbital sets that I have on my ligands. If I go through, and I can do the same thing on my metal. Now remember my metal, I have my S, my P, and my D also. Yeah, blue's okay with this. Yeah. Sorry, I'm trying to keep stuff color-coded. What I'll find out is on my metal, I have my S orbital, which is A1G symmetry. My P orbitals are going to be T1U, okay, and my D orbitals are going to be EG and T2G, okay? Now, how in the world did I get these? I have to use something called a character table, okay? And take a look at some of the other videos that I posted for you guys online. It shows exactly how they get these things out of there, okay? Do I need you guys to know how to get these? No. Here's what I need you guys to be able to recognize. I need you guys to be able to look at something like A1G and say, aha, I know that that is referring to an orbital, okay? I need you guys to know what the T and the E and all this, these kind of basic part of these mean, okay? Now here's what we're going to do. Now we play the matching game. So symmetry has to be maintained, right? We can only overlap orbitals of the same symmetry. So if I want to use my S orbital on my metal, and it's A1G symmetry, then I better have an A1G set on my ligands, otherwise a bond won't form. Okay, so A1G can overlap with A1G. T1U, right, can overlap with the T1U. The EG can overlap with the EG. Okay. And then what we see here is my T2G, right? That can't overlap with anything. It's of a different symmetry. We can't match, right? We can't match these letters together with anything there. All right, so let's visually represent this here then, okay? I'm going to take this exact idea, so pause and rewind here for just a second if you need to, right? And I'm going to take this exact same idea and I'm going to draw a molecular orbital diagram using those thoughts, okay? So bear with me here. Here are our, let's really color code this. I'm going to use ligands in red. I'm going to use my metal in blue. Let's start with the easier one, my metal here, okay. Let's see here. Here's my T1U set. These are my P orbitals, so the PX, PY, and the PZ. I'm not going to label those, and you guys will see why in a little bit. This is about to get pretty crowded. Here's my A1G, there's my S orbitals, and down here is my T2G, right, in my EG set, okay? Now I'm going to do the same thing for my ligands. These are technically all at the same energy, okay? But I'm going to just stack them up on each other. Just otherwise it gets pretty crowded, okay? Now the ligands are going to be, the orbitals are going to be lower in energy for the ligands than the metal, just because, right, if we're talking about chlorines versus metal, you guys can take a look at the periodic table and where things line up and all this kind of stuff, okay? So there is that idea there, all right? So now we play the matching game. Oops, oh my goodness. Sorry guys, this should have all been red over here. I don't know why I picked green. It's alright, we got some Christmas colors now. Okay. So now we play the matching game, right? A1G and A1G are going to come together to form a sigma bonding combination, okay? So here's my A1G, right? This is sigma, right? And if I want to connect the dots here, these will come together. And if I make a bonding combination, I'm going to make an anti-bonding combination. Okay, so A1G star. Okay. Now let me pause here for just a second and kind of just focus in on this, right? All I'm doing is matching the symmetry of the orbitals. What in the world does this orbital look like? Well, let's draw it out. It's my s orbital on my metal. Okay, my s orbital on my metal with an A1G set of orbitals coming in from my ligands. Now, I'm going to simplify this, and, if there's somebody not in this class who's watching this, just take a note, right? This isn't a full inorganic or organometallic course, right? So let's just say that the A1G set, like I'm looking for orbitals that can overlap with my s orbital on my metal. So I can use my s orbitals on my ligands. Okay? And so if you imagine, right, we bring the red and the blue together, right? Those will make a bonding combination to make a set of to make a sigma bonding combination, okay? But, right, now watch what I'm going to do. We can also use one of our p orbitals, right? We can also use one of our p orbitals on our ligands, okay? And so we would say that this is a hybridized, the arguments in the books and all this use hybridized p orbitals and all this kind of stuff, okay? So understand there's a little bit of other stuff going on behind the scenes. But this would be the visualization for that A1G set there, right? We have the s orbitals on the metal, the s orbitals on the ligands there coming together, okay? Cool. Now we move, right, here's our EG set, and here's an EG set. We're going to come down in energy here. Okay, so that's EG star, right? EG. Oops. Sorry, that's my bonding combination. Right, EG, right? And then it's going to go up in energy here, right? EG star. Okay, can you guys maybe draw what the EG orbitals, what these EG orbital bonding combinations would be? Remember, my EG comes from my x squared minus y squared and my dz squared. Okay, so if I take let's do the x squared minus y squared here. So orbitals, right, there's my axes. Let's draw my x squared minus y squared. Remember, they are on axis. Right, it's an on-axis orbital. So we could have a couple different orbitals on the ligands interacting with this. The s orbitals, the p orbitals, a set of p orbitals could come in and interact with this, right? And that would be an example of the EG, right? Similarly, right, if we have the dz squared, right? Right, here we could draw something like this, right, where the s or the p orbitals here are interacting in one phase, right, and then we have the opposite phase interacting at the top there, right? And that would be our bonding combinations, right, using either the s or the p orbitals. It doesn't, or actually, right, it'd be a hybrid of those two, is what it technically would be. I hope, the visualization is where it really starts to click together, right? If you guys can pause and visualize how these orbitals come together and what combinations, then you guys are really kind of learning months of stuff at once, right? But it's difficult, and there's a lot that I'm skipping. I get it, okay? Like I said, we're trying to keep it as simple as we can. All right. So we just finished our matching game here, right? The T1U set. T1U, right, T1U. Okay, that's coming here, and we'll bring that We'll bring that up here. Star, right? And so remember, this is our p orbitals on the metal interacting with the orbitals on the ligands themselves, right? Okay, so let's pause here for just a second. Oh, sorry. Let's do one more thing, okay? So now we've used our T1U, our EG, and our AG. The only thing that's left is our T2G. Well, nothing's interacting with it, so it's not going to change in energy. So this is a non-bonding. And you'll notice I'm keeping it blue, okay? And there's a reason for this. We'll talk about it here in just a second. All right, let's start to break down the different components of this. Let's take a look down here. Okay, so how many orbitals do we have? We got 1, 2, 3, 4, 5, 6. We've got 6 sigma bonding combinations. Does that make sense? Well, it should, okay. We've got 6 bonding combinations. Let's say, I'll redraw it here. Let's say that we've got iron hexachloride, right? So we got octahedral iron complex. Well, how many bonds do we need to bring this thing together? Well, we have 6 chlorines. They all need a bond, so we should expect to have 6 bonding combinations, and we do, okay? You're like, oh, that must be just a coincidence. No, that's how this works, right? Every bond must be represented somewhere, okay? If we have 6 bonding, we expect to have 6 anti-bonding combinations, and we see these up here also, okay? And here is something super duper important. The EG set, okay, the EG set in an octahedral complex is anti-bonding in character. It is anti-bonding in character. Oh my, okay. So that is going to be extremely important. It also means that the T2G set is non-bonding in character, and that's going to be important. Both the EG star set, okay, and the T2G set are metal-based. That means that these are more hanging out on the metal than they are on the ligands. And this is just a consequence of the closer in energy, okay, the closer in energy the orbitals are to their starting positions, right? That means they're hanging out more on that metal themselves, okay? And so all the magic is going to happen in the T2G and the EG set. And so the electrons that come in and out and get shuffled around and moved, right, they're either going to be coming into or out of the T2G and the EG set. And so in one of the subsequent videos, we're going to talk about the consequences of this. But what's important to recognize is that in an octahedral metal complex, the EG is an anti-bonding orbital and the T2G is non-bonding. And you need to know which are what, right? These are still my x squared minus y squared, okay, and z squared, mostly, okay? And I know. There's, like I said, I'm hand-waving a bit here, okay? And this is my xz, my yz, and my xy, okay? But this would be the molecular orbital diagram for an octahedral sigma-only complex. And I hear what you're saying. You're saying, wait a minute, we're missing electrons. You're right, okay? And that's going to be the topic for the next video, all right? We're going to talk about how we fill in the electrons. Now, once we know how many electrons there are, okay? Once we know how many electrons there are, then we can, just fill this in normally, right? We start from the bottom, work our way up. The ligand orbitals are typically always filled, right? So these are, we could pretty much assume that these are always filled here. All right, so we could just transfer these over. Whoops. The trickier part comes from when we deal with how many how many electrons are on the metal. And so we'll have to learn accounting, well, accounting in a way, and we'll have to learn how to count for that. Okay? Let's see. I think that's a pretty good pause here. Okay? So, very important molecular orbital diagram here. Lots of important concepts. Rewatch this video or watch some of the other stuff that I posted for you guys. It'll kind of expand this idea and kind of bring things out for you here, I hope. Okay?